There will be 4 free response questions on the AP exam. This video is modeled after FRQ number 4. It's primarily about trigonometric and logarithmic equations. Let's pretend it's from the 2008 exam. If you appreciate this content, please give it a like. These are the directions you will see on the AP exam for FRQ number 4. Pause the video and give it a read. Part A. Functions g and h are given by these expressions. A Part 1. Solve g of x equals -4 for values of x in the interval 0 to 2 pi. Setting g of x equal to -4 gives us this equation to solve. Ultimately, we must get x by itself, but let's start by dividing both sides of the equation by 2. So now we have this equation. Secant is the reciprocal of cosine, and I am far more comfortable with cosine, so let's take the reciprocal of both sides of this equation. That will turn secant into cosine, so we have cosine x minus pi over 3, and the reciprocal of -2 is -1/2. If you have not memorized these 9 trig values, pause the video and study it right now. At least get yourself to the point where you could write this chart on a piece of scratch paper from memory. We can solve for the expression on the inside by asking ourselves the cosine of what is equal to -1/2. Ignoring the negative sign for a moment, we see that the cosine of pi over 3 is +1/2. That means that pi over 3 is the reference angle. The solutions to this orange equation will be some multiple of pi over 3. The cosine of any multiple of pi over 3 will either be 1/2 or -1/2. On the unit circle, cosine is the x value, and in the first quadrant, x values are positive. That's why the cosine of pi over 3 is +1/2. 2 pi over 3 is in the second quadrant, where x values are negative, so the cosine of 2 pi over 3 will be -1/2. We are looking for the angles where cosine is equal to -1/2, not +1/2. So we've found one solution, 2 pi over 3. We know that cosine is equal to the x value on the unit circle, and x values are only negative in quadrant 2 and quadrant 3. So we can really ignore quadrants 1 and 4. On the interval from 0 to 2 pi, the only other solution to this orange equation will be in quadrant 3. We can think of pi as 3 pi over 3. So 2 pi over 3 is right before 3 pi over 3, and right after 3 pi over 3 is 4 pi over 3. The cosine of 4 pi over 3 is also -1/2. So 4 pi over 3 is the other solution to the orange equation on the interval from 0 to 2 pi. When you get really comfortable with this, you will do all of that in your head. When you get to this point in the solution, you'll say, okay, I can find the value of the stuff on the inside by asking myself the cosine of what is equal to -1/2. I know the cosine of pi over 3 is equal to +1/2, so I need multiples of pi over 3. Cosine is negative in the second quadrant, that would be 2 pi over 3, and cosine is negative in the third quadrant, that would be 4 pi over 3. So you just get right to here. However, cosine is a periodic function with a period of 2 pi, so there are actually infinitely many solutions to this equation. Adding or subtracting multiples of the period will give you the same output value. So if x minus 3 is equal to 2 pi over 3, it will also be equal to 2 pi over 3 plus 2 pi k, where k is any integer. Same thing with 4 pi over 3. X minus 3 will also equal 4 pi over 3 plus 2 pi k, where k is any integer. We still need to get x by itself, so we need to add pi over 3 to both sides of the equation. When we do so, we will add it to both sets of solutions. I would normally just do this in my head, but I'm showing it for instructional purposes. Adding pi over 3 to 2 pi over 3 gives us 3 pi over 3. So we end up with x is equal to 3 pi over 3, or simply pi, plus 2 pi k, and 4 pi over 3 plus pi over 3 is 5 pi over 3. So that's 5 pi over 3 plus 2 pi k. Finally, we need to limit ourselves to values of x in the interval from 0 to 2 pi. So let's play around with the value of k until we get all of the solutions. At k equals 0, these terms disappear, so we are left with x is equal to pi and x is equal to 5 pi over 3. Both of these values are in the interval from 0 to 2 pi, so we have two valid solutions so far. At k equals 1, we get pi plus 2 pi, which is 3 pi. And then we have 5 pi over 3. Now, k is 1, so we have to add 2 pi. But let's think of this as 6 pi over 3. So that's going to make 11 pi over 3. However, 3 pi and 11 pi over 3 are both outside the interval. Let's try going the other way. How about at k equals -1? In that case, we would have pi minus 2 pi, and this is going to give us x equals negative pi. That's outside the interval. But what about 5 pi over 3 minus 2 pi? Well, let's think of this as 5 pi over 3 minus 6 pi over 3. That's going to give us negative pi over 3. That is also outside the interval. So the only solutions on the interval from 0 to 2 pi are pi and 5 pi over 3. So x is equal to pi or x is equal to 5 pi over 3. You don't have to show the work that I've shown here in red, purple, and green. You can do as much of this in your head as you're comfortable with, but you should show all the rest of this work. A, Part 2. Solve h of x equals 1 for values of x in the domain of h. This is the expression we were given for h of x. So, setting h of x equal to 1 gives us this. We need to solve this equation for x. The subtraction property of logarithms tells us that log a minus log b is equal to the single log of a divided by b. Similarly, the log of x plus 2 minus the log of x plus 1 can be written as the single log of x plus 2 divided by x plus 1. So now we have this equation. We can cancel out the log base 3 by dropping a base 3 on both sides of the equation. These are inverse operations, so base 3 and log base 3 cancel each other out, leaving behind the x plus 2 over x plus 1 on the left side of the equation. On the right side, we have 3 to the 1 power, which is equal to 3. Multiplying both sides of this equation by the denominator leaves us with x plus 2 on the left-hand side, and then 3 times x plus 1 on the right-hand side. Distributing the 3 gives us x plus 2 is equal to 3x plus 3. Now it's down to basic algebra. Let's subtract x from both sides of the equation. That's going to leave us with 2 is equal to 2x plus 3. Now let's subtract 3 from both sides. Now we have negative 1 is equal to 2x. Dividing both sides by 2 gives us x is equal to negative 1/2. We must be careful with logarithms to check for extraneous solutions. You cannot take the log of a negative number or even 0. So we must make sure that plugging negative 1/2 in for x does not give us a negative number or 0 inside of any logarithm. Plugging negative 1/2 in right here leaves us with positive 1.5. That's fine. Plugging negative 1/2 in right here leaves us with positive 1/2. So this is the solution to A part 2. Part B. The functions j and k are given by these expressions. B part 1. Rewrite j of x as a product involving secant x and cosecant x and no other trigonometric functions. You need to memorize the definitions of these three trig functions if you don't already know them. Secant x is equal to the reciprocal of cosine x. Cosecant x is the reciprocal of sine x, and cotangent x is the reciprocal of tangent x. Sometimes it's helpful to rewrite everything in terms of sine and cosine. For example, we know that tangent x is sine x divided by cosine x. Cotangent is the reciprocal of tangent. So if tangent is sine x over cosine x, then cotangent x will be cosine x over sine x. Let's get like denominators and add these fractions together. We can make like denominators by multiplying the first fraction by sine x over sine x. This is valid because sine x over sine x is really just 1. Dividing anything by itself is 1, and multiplying by 1 does not change the value of the expression. Similarly, multiplying by cosine x over cosine x is also just multiplying by 1. But notice that now we have like denominators, sine x cosine x and another sine x cosine x. When you have like denominators, you can add the two fractions together using the common denominator and adding the two numerators together. Notice that sine x times sine x is sine squared. Cosine x times cosine x is cosine squared. So on the next step we have j of x is equal to sine squared x plus cosine squared x over the common denominator of sine x cosine x. If you haven't already learned this, here's an important formula that you need to memorize called an identity. Sine squared x plus cosine squared x is always equal to 1. So we see the sine squared x plus cosine squared x in the numerator. We can substitute this with the value of 1. That gives us j of x is equal to 1 over sine x cosine x. We can easily split this up into two separate fractions. This single fraction is equivalent to 1 over sine x times 1 over cosine x. But 1 over sine x is cosecant, and 1 over cosine x is secant. So let's make those substitutions. And that's it. J of x is equal to cosecant x times secant x. We have rewritten j of x as a product involving secant x and cosecant x and no other trigonometric functions. B part 2. Rewrite k of x as a single natural logarithm without negative exponents in any part of the expression. Your result should be of the form natural log of expression. One of our logarithm properties is that c times the natural log of a will equal the natural log of a to the c power. In other words, you can move a number from the front to the exponent of a logarithm. So we can move this 3 to the exponent, and we can move this 1/2 to the exponent. So k of x is equal to this expression. Quick side lesson. If you have the sum or difference of multiple log terms, you can combine them into a single log in one step. The presence of these minuses tells me that it's going to be the log of a quotient. So there's my fraction bar. Each one of these terms will result in a factor in this fraction. Any term that is positive will give me a factor in the numerator, and any term that is negative will result in a factor in the denominator. So because natural log a is a positive term, I will have an a in the numerator. Because the next term is negative, the b goes in the denominator. Next I have a positive term, so the c goes in the numerator. And finally we have a negative term, so the d goes in the denominator. Similarly, I can rewrite k of x as the single log of a quotient. There are 3 terms, so there will be 3 factors in this quotient. The first term is positive, so x to the 3rd power will go in the numerator. The middle term is negative, so x plus 4 to the 1/2 power belongs in the denominator. The third term is positive, so the 2x minus 1 goes in the numerator. This is one version of the answer. It is a single natural logarithm without negative exponents in any part of the expression. However, we know that something raised to the 1/2 power is the same as square root. So this would be another version of the answer. Part C. The function m is given by m of x equals sine x plus cosine x quantity squared. Find all input values in the domain of m that yield an output value of 1/2. Finding input values that give you an output value of 1/2 is a long way of saying solve m of x equals 1/2. Setting m of x equal to 1/2 gives us this. When you square something, it means multiplying that thing times itself. Sine x plus cosine x squared is the same as sine x plus cosine x times sine x plus cosine x. Let's multiply this binomial times the other binomial. Sine x times sine x is sine squared x. Sine x times cosine x is sine x cosine x. Cosine times sine is another sine x cosine x. And cosine x times cosine x is cosine squared x. And all of that is equal to 1/2. These are like terms in the middle. Sine x cosine x plus sine x cosine x is 2 sine x cosine x. I'm also going to rearrange this a little bit to put the sine squared and the cosine squared right next to each other. So we end up with sine squared x plus cosine squared x plus 2 sine x cosine x is equal to 1/2. Whoops, I left off an x. Here's an identity that came up earlier in the video. I need you to memorize that sine squared x plus cosine squared x is equal to 1. So we can replace this part of the equation with 1. But here's another formula that you need to memorize called a double angle identity. 2 sine x cosine x is equal to the sine of 2x. So we can make that substitution as well. We will be left with 1 plus the sine of 2x is equal to 1/2. Let's isolate the sine of 2x by subtracting 1 from both sides. 1/2 minus 1 is negative 1/2. We can solve for the 2x on the inside by asking ourselves the sine of what is equal to negative 1/2. Let's see who's memorized the chart that I showed you earlier. Ignoring the negative sign for a second, the sine of what is equal to positive 1/2. Hopefully you just said pi over 6. That tells you that the reference angle is pi over 6. If you forgot the chart, let me show it to you. To answer the question, the sine of what is equal to negative 1/2, we start with the sine of what is equal to positive 1/2, because that is on the chart, and the sine of pi over 6 is positive 1/2. That just tells us that the reference angle is pi over 6. The real answer will be pi over 6 or a multiple of pi over 6. These are the 4 angles with a reference angle of pi over 6. There's one in every quadrant, above and below the x-axis. The sine of any of these angles will be either positive 1/2 or negative 1/2. We want sine to equal negative 1/2 specifically. We have memorized that sine of an angle is equal to the y value on the unit circle. So in which 2 quadrants will the y values be negative? That's quadrant 3 and 4. So those are the 2 quadrants that we need to find the solutions in. Here on the left is pi, and we can think of this as 6 pi over 6. Doubling that, 2 pi can be thought of as 12 pi over 6. If this reference angle is pi over 6, then we have 6 pi over 6 plus 1 pi over 6, which is 7 pi over 6. This angle is also pi over 6, so we have 12 pi over 6 minus 1 pi over 6, which is 11 pi over 6. These are the 2 solutions. Remember, we were solving for 2x, so far we've got 2x is equal to 7 pi over 6 or 11 pi over 6. However, sine is a periodic function with a period of 2 pi, so adding multiples of the period will not change the output value. We still have to get x by itself by dividing everything by 2. Remember that when you divide a fraction by 2, you multiply the denominator by 2. So we have 7 pi over 12 plus 2 pi k divided by 2 is just pi k. 11 pi over 6 divided by 2 is 11 pi over 12. And again, 2 pi k divided by 2 is just pi k. Since there is no restriction on the value of x, this is the final answer. Except we should add where k is any integer. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.